Hello, hello. Absolutely packed house today for the Blockchain Oracle Summit. Very exciting stuff. So the title of my talk is Decrypt My Data Only When the Sky is Blue. And it follows on nicely actually from the prediction market talk we just had, because you could also have decrypt my data only when a particular prediction market evaluates to a particular outcome. But before I get into it, a little bit about myself. Started working in TradFi in 2013. Got into the blockchain space via the EOS hackathon in 2018. And since then, I've been working across digital identity and digital currency. And most recently worked at Protocol Labs on the DRAND team, doing verifiable randomness oracles. And in 2023, I founded Randamu, which does lots of interesting things built on the same technology that powers DRAND. We're a pretty small team, 5 cryptographers and devs mostly. We like to do hackathons, puzzling, and drink lots of fancy, expensive coffee. So if anyone has any recommendations for coffee in Buenos Aires, please let me know, because it's been a little bit dire so far. We built a Decipher network, which is the next iteration of DRAND. It's all about threshold cryptography in a generalized sense, so applying threshold cryptography to other new problems. And oracles and execution are one of those big problems. So we're going to first gain a high-level understanding of threshold cryptography, and then we're going to build simple protocols with it. And then we're going to use our new knowledge to build seemingly impossible protocols like how can I decrypt some data when an oracle says the sky is blue? So what's threshold cryptography? Well, today we'll be talking of a T of N signature scheme, which, like all things cryptography, has a very inscrutable name. But in essence, well, a signature scheme, I guess most people are familiar with. You have some private key, you sign things with it, and people who can have your public key can verify that the signature is authentic, that you in fact signed it. The T of N part basically means that we have N different signers, and we need T of them to work together in order to create a valid threshold signature. So we've got 7 dwarfs here. If 4 of them create signatures, together, those signatures will form a valid signature for the entire set of 7 dwarves. Additionally, any group of 4 dwarves who sign will come up with the same signature, and this has some interesting properties that we'll get into in a little bit. So intuition on how this works, it's a little bit like drawing a line collaboratively. So if you imagine we've got n equals 3 this time, Alice, Bob, and Carol, and we have a threshold of 2, so we want to draw a line together, but with one single point, we can't actually draw, well, we don't know that we can draw the correct line, because from a single point there are an infinite number of lines going in an infinite number of directions, so we can't possibly be sure with a chance greater than a chance that we're going to draw the correct line. But if we were to get a single point from another one of the people on our committee, so Bob or Carol, we know the full line basically, so we can draw a line that intersects both our points, and it will be the correct line for our committee. Similarly, if we get Carol's point, it will be in the same line, because that's how a line works, or at least a straight line, I should say. I guess a curved line might be a bit different. And similarly, if we get just Carol's point, we will draw the same line as if we had our point and Bob's point. So today we'll also talk about aggregatable signature schemes, which in essence is taking this signature from the 7 dwarves and sticking it together with other signatures from other sets of 7 dwarves, such that we end up with one final signature that we can verify all the different committee signatures all in one shot. This is pretty nice, as we get a bit of a Frankenstein signature at the end. This is pretty nice because it saves us a lot of gas when doing things on chain. We can have a lot of different committees, for example, prediction markets, for example, different oracles, pulling different sets of data, and we can verify the result just in one go. Another interesting property of the signature scheme is that when we get a valid signature for a committee, we can't actually attribute that signature to individual parties in the committee. So back in our 7 dwarves example, we know that 4 at least of the dwarves signed to attest to something, but we don't know which 4 did it. So for some privacy-related protocols, that can be quite important. And if threshold is more than 50%, it's basically an honest majority consensus. So kind of a lot of blockchain-y stuff boils down to, have you got a majority consensus? So we can do that without the blockchain. Another interesting property is if we have a threshold lower than 50%, we can have multiple disparate groups come up with the same signature. So if you imagine, I thought I had a slide in there, but if we had a threshold of 2, for any set of 2 dwarves in our 7 dwarves, we could come up with the same signature, even if they weren't connected to one another, which is interesting for poor network scenarios. So how do we make this happen? Well, firstly, everyone needs to get a key share in order to make that happen. So we perform a protocol called distributed key generation. In essence, we do a fancy protocol where we pick a polynomial, we evaluate it at a point for each of our 7 dwarves, and we send those 7 evaluations to each one of the other dwarves. Everyone else does that. They pick a polynomial, they evaluate it 7 times. We each get 7 evaluations for each of the polynomials, and using that we can interpolate some other polynomial that nobody has, and that's secret. So that's the secret key. The secret key is never in memory, so nobody can use it unilaterally without the other 4, with at least the other 3 dwarves getting on board. So we can use it to build higher level protocols. The first protocol we built with this was DRAND, so it's an oracle for verifiable randomness. Basically, every unit time, DRAND ticks with a new signature. So signatures map to wall clock time. Each node in the network is attesting to the fact that some wall clock time has been reached. And they sign a message, which in this case is just the epoch number, which reflects some wall clock time. We exploit the fact that without the secret key, nobody can predict what a future signature is going to look like. Otherwise, the signature scheme would be kind of useless because we could just forward signatures for other people's keys. So therefore, the signature, if you don't have the private key, is as good as random. So because nobody has a private key, it is basically randomness. Oh, hello, Dylan. I see you just popped in. Nice to see you. On top of that scheme, we built a thing called time block encryption. So we realized that because we knew what all the future messages were going to be, due to the properties called pairings in this particular threshold scheme, there's a relationship similar to a public and private key between the message that's going to be signed and the signature at that future time. So it's a thing called identity-based encryption, and it's based on this fancy maths, which we're not going to go into because I've only got 6 minutes 45 left. But in essence, like I said, there's a relationship like a public and private key. That future message, so 1237 in the bottom here, becomes like a public key, and the decryption key becomes this signature that gets emitted at epoch 1237. So yeah, similar to traditional trapdoor asymmetric cryptography that we're all used to. Excellent. Taking that a stage further, that allows us to use one particular oracle, DRAND, in order to do time lock encryption, because DRAND kind of reports the time in a very roundabout way. But if we were to instead base it on real-world conditions, we could start decrypting data whenever real-world conditions are met. So take the same identity-based encryption, but instead of encrypting the time, we pose questions to Oracle networks. So for example, first I got to apologize that this particular image is an editable text, and some Philistine used the British or the American English spelling of color around the British English spelling. So I apologize profusely. I'm disgusted, but I didn't have time to change it. But anyway, we pose a question to an Oracle network, such as what color is the sky? And we can use the resulting answer that we're interested in to encrypt our data. So here we've got a blue padlock. When the sky is blue, we'd like our data, hello world, to be decryptable. So we encipher the data using our public key, the color blue, in some formation. And if our Oracle network evaluates the fact that the sky is gray, that's no use to us. We can't use that as a secret key, but if they were to say the sky's blue, we do this fancy pairings again that we saw before, similar to DRAND's track of the time, and we can decrypt our data and get the result back. With that, you can actually build a whole bunch of other interesting protocols. So we built a swap protocol, only swaps on top of that, which allows you to swap based on certain conditions. Choose your committee of people you'd like to evaluate these conditions, like is the sky blue? And that way you can actually get distributed oracles nicely. You can rely not just on one oracle provider, but multiple oracle providers at once for increased assurance. You can also do things like schedule upgrades for your contract. So if an oracle says my upgrade is safe, for example, or if an oracle says that I passed a security audit for a given implementation, you just basically format a message of a specific taxonomy and get some committee to sign it, attesting the fact that that's safe. So yeah, that's basically everything. You can use Oracle data to decrypt different ciphertext that you've got, and that unlocks a whole wealth of new protocols. You can do things like on-chain order books. You could do things like encrypted data that unlocked by prediction markets, and that's very exciting. So give us your data, and we can build seemingly impossible protocols. And I'll open the floor to any questions, if anyone has any. Going once, going twice. Thank you very much.